Okay, so for this video, let's go back to the time-independent perturbation theory and consider a quantum mechanical system with 4 states and whose Hamiltonian is given by this thing over here, right? This matrix. So here in this matrix, you can see this V naught over here. It is a constant potential, and the epsilon in the matrix is a term that characterizes the perturbation of our system. And so epsilon will be much smaller than 1, right? It's a very small term. Okay, so let me first start off by writing that my Hamiltonian can be written actually as a sum of my unperturbed Hamiltonian plus some perturbation term, right? So the perturbed Hamiltonian. And so what we're going to do for this is let's find the corrections to the energy of the energy eigenstate, right? And so we're going to do that using the time-independent perturbation theory, as our potential or the Hamiltonian is not a function of time. It is a constant matrix or a constant potential. So for the unperturbed Hamiltonian, right, it is obvious that we will set our epsilon, the term that characterizes the perturbation, as equal to 0. So that will imply that there is no perturbation in my system, and so for unperturbed my Hamiltonian can be written as the following. So let me write it with H naught being equal to, right? So all I have to do is set my epsilon is equal to 0, so I'll have 3 over here. Epsilon is 0, 0, 0. Again, epsilon 0, 3, and 2 times epsilon, and epsilon is 0, so 0, 0, 0, 2 times epsilon, again 0, 5, 0, right? 0, 0, and epsilon is again equal to 0, so 0 and 7, right? So all I have done here is, in my original Hamiltonian, I have replaced epsilon with 0 for unperturbed Hamiltonian, and therefore I got this expression or this matrix right over here. Okay, and actually let's not forget that we'd have a V naught over here, right? So yeah, this is it. Okay, so from if you look at this Hamiltonian, it appears to be, it is diagonalized already, and so for if this Hamiltonian is diagonalized, it is obvious from the Hamiltonian that what our eigenenergies would be for the unperturbed case, right? So they would be the diagonal elements of this Hamiltonian, and so we would have I'll write it over here, right? So we would have E 0 subscript 1 will be 3, E 0 subscript 2 will be 3 again, and so we can see we would have degeneracy, right, in this degenerate states, and we would also have E 0 3 being equal to 5, and E superscript 0, that just stands for that it's unperturbed. Fourth would be 7, right? Okay, so we have figured out the unperturbed eigenenergies, right? And all of these eigenenergies would have V naught with them, right? So V naught, V naught, V naught, V naught, right? Okay, so and also we can figure out what the eigenvectors are, and because it's a diagonal Hamiltonian, so it's pretty much obvious. So for this thing over here, we would have my eigenvector 1 0 0 0. For the next one over this, I would have 0 1 0 0 and so on, right? Okay, so actually let me go on next page and write those down. So my eigenvectors or eigenstates would be psi1 would be represented as a matrix that is 1 0 0 0. Psi2 would be represented as 0 1 0 0, right? And my psi3 state would be represented as 0 0 1 0, and likewise my psi4 would be represented as 0 0 0 1. Alright, okay. So now because there is degeneracy, right? So first what we shall do is solve for the non-degenerate states, and those states, if you go back over here, look at your energy, the non-degenerate states are my E3 and E4, right, corresponding to energy values of E3 and E4. So first what we will do is solve for the non-degenerate states that are psi3, psi4, right? Okay, so for these I can use my non-degenerate perturbation theory, right? So NDPT. Okay, so first we shall again recall that my Hamiltonian can be written as my original unperturbed Hamiltonian plus the perturbation Hamiltonian, right? So if that's the case, then I could write my perturbed Hamiltonian as following, right? So all I would have to do is from my original Hamiltonian subtract the unperturbed Hamiltonian. So let's go back here. This over here is my original Hamiltonian, right? And this is the unperturbed Hamiltonian. Okay, so you have to just subtract from your original Hamiltonian the unperturbed Hamiltonian, the matrix elements, and so you would get your H1 as the following, right? So 0 epsilon 0 0 epsilon 0 2 epsilon 0 0 2 epsilon 2 epsilon, having trouble writing that down. Okay, 2 epsilon, we have 0 epsilon, and then 0 0 epsilon 0, right? Okay, so this is now the Hamiltonian, that is the perturbed Hamiltonian, and we'd have a V naught over here, right? Okay, so for computing now the correction to the eigenenergies, right, let's first look at the first order energy eigencorrections. So this Hamiltonian is going to be important for that, right? Because if you remember, the first order energy corrections is nothing but the expectation value of this Hamiltonian right over here, right? The perturbed Hamiltonian. And so if you look at this Hamiltonian, you can see that what would be the expectation value, right? So the expectation value in psi 0 states, right? So let me just write that down over here. How is it given? So E n to the first order is actually the expectation value in psi n states that are 0th order of my perturbed Hamiltonian, right? So this is how it's given. Okay, so we are going to do for states 3 and state 4, right? Because those are the non-degenerate states, and we're using non-degenerate perturbation theory for those states. So then I'll have for my psi n's as my psi 3 and psi 4. So if I do that, then I could write my E1 3, right, as 3 H1 3, right? So the matrix element, this one, right? So if you look at your perturbed Hamiltonian, what is this matrix element, right? It's 0. So it's 0. And similarly, if you do this for the state 4, you can see from your perturbed Hamiltonian, this thing over here, that is also going to vanish. So your correction to first order corrections to your energy is going to vanish, right? So we could say that the first order energy correction is actually the vanishing order, right? Because the corrections vanishes. Okay, so then what should we do is, let's go ahead and compute the second order energy corrections, right? And so to do that, again, we know that those are given by E2n, right? Those are the sum of my m naught equal to n psi n unperturbed, and then I have perturbed Hamiltonian psi m unperturbed states, and then I have the square of this thing over here, modulus square, and divided by E0n minus E0m, right? So if you don't know where this thing came from, you should go back and watch my previous video on the perturbation theory. In that video, we derived the first order and second order energy corrections, as well as the first order correction to the eigenstates, right? Okay, so now all we have to do is we are going to compute this, right? So how are we going to do that? Let's write it that E for state 3, let's do it for state 3 first. So that would be simply where my m is not equal to, because we're doing for state 3, so n over here is state 3, so m is not equal to 3. We're going to sum over all such states, right? So 3 0 h1, and I have over here my psi m, right, 0, square of this thing, and I'll have my E 0th order 3 minus E 0th order m, right? Now you just have to look for such states where your m is actually not equal to 3, so those are state 1, state 2, and your state 4, right? And so then we would sum over all those states, and that would simply be, let me write it down, right? 3 0 h1, first let's do for states 1, right, squared, and I would have my, okay, now for the energies, what is your E3, right? If you go back to this slide over here, you can see that your E3 is this thing over here, right? Yeah, it's this thing over here, right? So E3 is your 5 times the potential V naught. So, and your E1 is 3 times V naught. So let's go back and let's put the values for E3, that is the perturbed, unperturbed energy is 5 V naught, and we're first doing it for m equals 1. So for that state we have 3 V naught, 3 V naught, right? So 5 minus 3 V naught. Okay, now we would sum for the others, right? So again 3 0 H1. Now we would have 2, right? 0. Remember that we have to have those values of m which are not equal to n, and for E3 n is equal to 3, and so therefore the values of m are going to be 1, 2 and 4, right? Okay, so likewise we would have here E3, that would be 5 minus m is 2, so E2 it was my 3 V naught again, so I would have this thing over here. Now for the fourth state, so we would have this thing 4 squared, right? And again 5 minus what is E4? E4 was 7 volts, right? Or 7 times V naught actually, right? So this is what we would have. Now all we have to do is compute these matrix elements and square them, right? And so we would have the second order correction. Okay, so to compute these matrix elements is actually really simple. You have to go back to your perturbed Hamiltonian and look for the matrix element 3 1, right? For this first term, and for the second term you have to look at 3 2, and for the third term you'll have to look at 3 4, right? So let's go and see how we would do that. Okay, so let me use a highlighter, let's see, right? Okay, so let's say that you have to first let me go back here. Yeah, for 3 1, right? This is your perturbed Hamiltonian over here in the box, right? So what would be 3 1, right? So your third row, first column, right? So third row and first column, so that would be this thing over here, right? 0. And then you have your third row and second column, right? So that's this thing over here, and third row and fourth is this thing right over here, right? So these are going to be your matrix elements that you're going to substitute over here. And so once we do that and we compute this thing over here, what we get is 3 over 2 squared V naught, right? And this is now the E3 correction, right? Second order correction to E3, right? Okay, so let me just box this over here. Now let's compute for E4 to second order, right? Okay, so let's go ahead and do that over here. So for E4 to second order, right, is again we will use the same expression for second order corrections, right? And so because we are computing for E4, so n is going to be 4, and m not equal to 4 will be all such states where I would have 1, 2 and 3, right, and not 4. So let me just write it down directly over here for this now, that this would be 4 0 H1. Now I would have 1 over here, right, over E4, or let me just write down the values, right? So you know how to do this now, right? 7 minus 3 V naught, right? These are the eigenenergies of the unperturbed Hamiltonian. and I would have plus, again my n is 4, so I would have 4 over here, h1, and remember that your m is not equal to 4, so I would have 2 over here squared over 7 minus 3 v naught. I'd have another term that would be 4 h1 3, right, over 7 minus 5 v naught. Okay, so I have not written for these 4 2, right, I have not written the superscript 0 because now it's understood that these are the unperturbed states, right? And so again it is very direct to compute the matrix elements by looking at the perturbed Hamiltonian and squaring them and putting them in this expression over here. And when you solve that, right, so what you get is that your second order E4 is actually 1/2 epsilon squared v naught, right? Okay, so we have also computed now for E4, and so therefore we have computed our eigenenergies that are non-degenerate, right? So what we could write now our E3 and E4 as, right? So your what would be your E3? So it would be 0th order correction, that was 5v naught. Then your first order correction, that was 0, so let's ignore that. And then your second order correction, that was plus 3/2 epsilon squared v naught, right? And similarly for your E4, that would be your 0th order correction, that was 7v naught from the unperturbed Hamiltonian, right? And then your first order correction, that was again 0, and now your second order correction, that was 1/2 epsilon squared v naught, right? So we have here, we have our E3s and E4, right, corrected up to second order. Okay, so now let's look at the degenerate states. So for the degenerate states, they are in 2×2 space, right? So if you go back, so here we have only 2 states that are non-degenerate, and the other 2 states are then going to be degenerate states, right? That is that we've found from these energy values corresponding to those states for E1 and E2, that were 3v naught. So state 1 and state 2 would then be degenerate states, right? And so therefore they are in a 2×2 space because there are two such states. So then what we should do is we should diagonalize our Hamiltonian for a 2×2 space, right? And so first let's recall that the Hamiltonian was as such: v naught 0 epsilon 0 0 epsilon 0 2 epsilon 0 0 2 epsilon 0 epsilon 0 0 epsilon 0, right? Okay, so to write this for a 2×2 space, it's actually pretty obvious. That would be for states 1 and 2, right? It would be represented as v naught, this term over here, right? So this and this. So what is that? 0 epsilon, right, and epsilon 0, right? So Now our next task is then to compute the eigenvalues of this matrix element over here, and we can, that is actually pretty obvious from your linear algebra course. So that's actually done by this thing over here, that you write your determinant of h prime, right, 1 comma 2, these are those two states, minus lambda times the identity matrix, right, is set that equal to 0. And so you compute your lambdas over here, and the lambdas would then be your energy eigenvalues, right? And so when you solve this equation using this thing, right, when you solve this, what you get is you get your energy eigenvalues as lambda plus minus, or your plus minus epsilon v naught, right? So these are the two energy eigenvalues that you get, and so from here then you can simply write your corrected energies as let me do that over here, right? Okay, so then you can simply write it your E1 as the 0th order correction plus the first order correction, right? And then that would be, the first order correction is this term that we got from here, right? So plus epsilon v naught, right? So we can then write it as the 0th order correction was 3v naught, right? And the first order correction is plus epsilon v naught, right? So this is then your E1 corrected up to first order, and similarly for your E2 up to first order would then be your E2 as 0th order was 3, remember, degeneracy, and the first order correction is negative epsilon v naught. So this over here is then your correction to your energies using the time independent perturbation theory, right? So we, in this example, what we saw was how do we use the time independent non-degenerate perturbation theory to solve for a quantum system whose Hamiltonian is provided or known to us. And then we also saw that how do we if that Hamiltonian or if that system has some degeneracy in it, how can we solve for the degeneracy using the time independent perturbation theory? And so this quantum system with 4 states was a time independent Hamiltonian, right? And so we used the time independent perturbation theory to find the corrections to the energy of each energy eigenstate. And we also found out what would be the non-vanishing order for each state. That was the first order for my E3 and E4, right? The non-degenerate states. So that was it for this video. I hope you understood how do we use the time independent perturbation theory for a system or a quantum system that has 4 states, or you could use this for a quantum system with n states now, right? And solve for it for the eigenenergies, right? Okay, so that's it.